Well, hello everybody. It's Dave here today to talk about our first of two lessons on this idea of uniform electric fields. Now, hopefully you've had some experience with point charges and non-uniform fields up till now, because a lot of the terminology that we're going to use today is going to involve those concepts. So if we think about our previous exposure to these concepts, we'll start off with a simple point charge. And when we map the electric field, we know that we would draw arrows radially outward. Remember that we do this because we're imagining a positive test charge and the direction that it would go given its interaction with the other positive charge. And so in this case, we also learned that the field actually decreases at a rate of 1 over r squared. In fact, kq over r squared was the equation that we came up with for this relationship. Now, the problem with that is that if we're at one distance away from the positive charge and we move to a different distance away from the positive charge, we'll end up with a different field strength. Therefore, it is non-uniform. What we would rather have is a situation where we have two plates, and let's make this plate positive and that plate negative, and the resulting field would actually be a very nice uniform electric field. Now, if we think about this from a charge perspective, let's say that we had some sort of positive charge at the positive plate, and we had a hole for that charge to be able to get into that plate. Well, what would happen now is it would be repelled from the positive plate and it would be attracted to the negative plate, which means its resulting motion would be in that direction, and it would continue to accelerate through this particular field until it got down to the other plate at the bottom, in which case it would then fly through the hole on the other side and continue on its way. This is an important element to consider a comparison to gravitational fields, because right now you are all sitting in a room where there is this microcosm of the entire gravitational field of the Earth. We know that if we go back to, say, the moon and we take a look at the gravitational field of the Earth, it's a non-uniform field at a rate of 1 over r squared. However, within your room, there is nowhere within that room that you're going to feel a different gravitational field, which means that all of the laws and relationships that we understand in the concept of acceleration and motion is going to be a very similar discussion when we deal with the motion of these charges. Because it's a uniform field, things like projectile motion and conservation of energy will still now apply in a very similar relationship that we've seen in the past. So to derive our equation for a uniform field, we're going to again start with the analogy of an object in a uniform gravitational field, just like your room. And let's say that we have a block that's at a certain height and it's going to fall to a second height. We would say that at the initial height it has some sort of initial potential, and at the bottom it has some sort of final potential. Now again, this could be that it hits the ground and we've stated that that potential energy at that height is 0, or we could relate it all to the center of mass, which in our case would be the center of the Earth. Either way we go, we know that there is a uniform field in the process of this drop. We're going to say that the drop is significantly low so that there is no change in gravitational field strength between the two. Well, if that's the case, then what do we know? Well, we know that the box is going to fly from a higher potential to a lower potential, and as this is happening, conservation of energy tells us that this energy is now going to be converted into kinetic energy. Remember that one of the nicest things about kinetic energy is the equation that we know works for almost all cases in dealing with slow speed objects, slow speed being a significant fraction lower than the speed of light. If we talk about this in terms of work, we know that because it is doing what it naturally wants to do, that it actually has negative work being done on it, as opposed to if we take an object and we do something that it doesn't want to do, which in that case would be lifting it up to a different height, we would actually have to add energy to the system, which would result in positive work. So taking these scenarios into account, now we can deal with the same concept in dealing with this idea of a parallel plate. Let's take a positive charge, and let's say that we're starting it from a higher potential, and what's going to happen from the higher potentials, because it's positively charged, it's going to fly towards the lower potentials. So we still have a uniform field that looks like this. But now what's going to happen is that object is going to accelerate from rest until it reaches the other plate. And in the process, what's going to happen? Well, it's going to convert whatever initial potential energy it has. So it has some initial potential, and it will have some final potential by the time it has completed this particular flight. And in the process, what's going to happen is it's going to gain kinetic energy, just like it did in the gravitational case. Well, that's fantastic, because that means that if we can somehow relate this change in potential to the electric field, we're going to be able to find out just how fast it's going. So you're going to want to remember, of course, that we have some distance that we are flying. And we also know from previous experience that the work being done on the charge is actually equal to Q delta V. You'll notice that in this case I've excluded the negative sign. But keep in mind, of course, that when we're dealing with energy and we're dealing with work, we are going to determine what the direction is. But generally speaking, is if the object is going to do what it wants to do, then the work being done on the object would actually be negative, because you'd have to release energy to cause this to happen. At the same time, if we were moving the positive charge from the negative plate to the positive plate, we would have to add energy to the system, because it wouldn't naturally want to do that. And so taking these ideas into consideration, we now have the base equation that we can use to find what the electric field is in the uniform case. So the first thing we have to recognize is that we have two definitions of work. We know that we're dealing with potential energy, and we also know that there's an equation that relates it to the applied force times the distance traveled. Well, in this case, the applied force is actually equal to the electric force, which is equal to QE. Okay, well, we have that, and we also know that our change in potential energy, specifically electric potential energy, is equal to Q delta V. And again, this is from previous lessons. Well, if we put these two ideas together now, Q is delta V is equal to QE times D, something great happens. The charge itself cancels out. And we end up with an equation now that relates the potential difference between the plates to the electric field strength, which we are considering uniform. Now, this equation is a great equation because it will actually give us the electric field strength between two parallel plates with a potential difference of delta V and a distance between them of D. There's an important statement that needs to be made, and it's the idea that this equation actually only holds when the distance between the plates is much, much smaller than the area of the plates themselves. There is a lot of physics going on here that we're not going to get into because it's all based upon a higher level content. But the basic understanding that you need to get here is that there is a uniform charge distribution across the plates. And in order for this uniformity of the electric field to be confirmed, there has to be this small, small distance in between compared to the area of the plates themselves. All right, so let's take a look at an example involving this equation. And we're going to calculate the field strength given the distance and given the potential between the plates. The first thing I'd like to do is actually draw a set of parallel plates. And I'm going to go ahead and label these according to the voltages, so 6 volts and negative 6 volts. Now, we know from the previous discussion that the actual field will move from a higher potential to a lower potential. So what we actually get is a situation that looks like this. Now, I have specifically not drawn the field lines right to the edge of the plates. And the reason for that is there's actually a phenomenon known as fringing that occurs at the edge of these plates. And so the actual field lines at the edge would look more so like this. But for the sake of argument with these types of problems, they don't consider those particular field lines in these problems. So when we're thinking of any sort of motion of particles, we're always talking about it right in the middle of the plates where no fringing is taking place. And so in this case now, it's a simple calculation of E is equal to delta V over D. We have our values. Now, we know that delta V is equal to final minus initial, but in this case, I want you to recognize the fact that we're just dealing with a scalar quantity. And when we're dealing with a scalar quantity, we don't really care about the negative sign in this case. We're going to deal with directions when it comes to understanding the nature of the charge and the direction of the electric field. So in this case, I just want you to take the actual difference. And if we go from a -6 to a +6, that's a difference of 12 volts. And we have our distance, that's 6 times 10 to the -2 meters. And that's going to give us an overall field strength of 200 newtons per coulomb. Now, an important thing to recognize is sometimes they give you the distance of the plates in meters, and sometimes they don't. Remember that we're dealing with SI units here, which means you absolutely have to have things in terms of meters, in terms of seconds, in terms of kilograms, if the mass is necessary. Okay, let's take a look at another problem now where we're actually going to take a particle and put it into this field and have it gain kinetic energy. We have an electron, and it's accelerated from rest through a potential difference of 3 times 10 to the 4 volts, and we want to know what the kinetic energy is after it goes through this potential. So when we're dealing with kinetic energy, just for the record, kinetic energy is 1/2 mv squared. So no matter what we're dealing with, unless we're dealing with something like relativity, we're going to use this equation to find things like the velocity of the particle, or if we have the velocity of the particle, maybe we find the mass of the particle. So what do? Well, let's go ahead and draw our parallel plates. Now the tricky part this time is the fact that they gave us the potential difference but not the potential on individual plates. The beauty is it really doesn't matter what potential you put on one plate so long as the potential difference across those plates is 3 times 10 to the 4 volts. What I like to do to keep things simple is put 0 potential on one plate and 3 times 10 to the 4 volts on the other plate. Based upon the way that I've labeled this, we know that the electric field is actually going to point from the higher potential to the lower potential. Now you'll remember that when we draw electric fields, we know that that represents the direction that a positive charge would travel. So in the case of an electron, we know that an electron, to experience the full potential difference, has to start from this plate and move to the right. And so when we're dealing with this idea, we have potential energy that's being converted to kinetic energy. We're dealing with the conservation of energy. And so in this particular example, the nice way to write this out is that the positive change in kinetic energy has to be the negative change in potential energy. Remember that that negative sign represents the fact that for one to increase, the other must decrease. This is the essence of the conservation of energy. Well, we have an equation for the change in potential energy involving potential difference, and you may recall that delta EP is equal to Q delta V. Well, this seems perfect for this case. So our change in kinetic energy is now going to be equal to negative, well, we have Q, which is negative 1.6 times 10 to the minus 19 coulombs, and we have this multiplied by our delta V, which is 3 times 10 to the 4 volts. And the result that we get is 4.8 times 10 to the minus 15 joules. And so it's not a surprise that the result here is a positive energy value because, again, this has been gained through the transfer of energy from the potential energy to the kinetic. So if we wrote this down just in terms of the change in potential, we would expect this to be the same magnitude, but a negative sign. All right, the last type of problem we're going to figure out now is let's actually take this whole concept of uniform fields, let's convert potential energy into kinetic energy, and then let's go ahead and find what the velocity of the particle is when it leaves the field. So the first thing we'll look at here is the diagram. It says a proton, this is important, initially at rest is released between two parallel plates as shown. All right, so we know just by looking at this diagram, and this is obviously not to scale because the distance looks humongous compared to the size of the plates, but obviously 0.025 meters is not very large at all. We know that if we draw the actual direction of the field, we know that the direction of the field is from high potential to low potential. And so the resulting motion of this particle is going to be towards the right plate. All right. And so what is the magnitude and direction of the electric field? Well, we have an equation for this now. We're just going to use it. E is equal to delta V over D. Well, delta V in this place is we have negative 400 volts up to positive 400 volts. That's a difference of 800 volts. And we have a distance of 0.025 meters. And that gives us a final answer of 32,000 newtons per coulomb. Now that we have that field strength, let's go ahead and find the electrostatic force acting on the proton. So for that, we go back to an equation, which I like to call the electrostatic version of Newton's second law. And we have that Fe is equal to QE. Well, we know what the charge is because we've been told it's a proton. We found the electric field strength in the previous problem, so we can simply plug these in. Remember that a proton and electron both have the same magnitude of charge. What's different is the actual polarity. And so one of the things, again, that's important about electrostatics is understanding how polarity plays a role in the overall direction of motion. We'll put in now the electric field strength, which was 32,000 newtons per coulomb, and we end up with an electrostatic force of 5.12 times 10 to the minus 15 newtons. And again, that sounds pretty small, but when we think about it, that's the force that's being applied to the object that is on order of 10 to the minus 27 kilograms. So that's really a substantial force. Okay, so for our last question, we're going to go ahead and actually find the velocity of the proton when it leaves the plates. As soon as you hear the term velocity, I want you to start thinking about the conservation of energy, which means we're going to deal with the positive change in kinetic energy is equal to the negative change in potential. We also know that we can find the change in potential if we use our previous equation of Q delta V. The other thing that's going to help us out here is to recognize the fact that there was no initial kinetic energy. We know that the object is initially at rest, which means the only kinetic energy that we're dealing with is the final kinetic energy. And now we can simply calculate the change in potential energy by plugging in our values for Q, which is 1.6 times 10 to the minus 19, and delta V, which in this case is going from a positive 400 volts to a negative 400 volts, which ends up being a negative 800 volts. Now you'll notice in this case I dealt with the negative signs, but I strongly encourage you that if you understand negative signs and what they represent in physics, which is almost always direction, either it be the direction of motion or the direction of transfer of energy, then you are more than welcome at some point to just explain the process that's going on here so that you don't make a mathematical mistake when it comes to these negative signs. If you ended up with a final kinetic energy that was a negative, that should be the red flag to let you know that you've made a negative sign error somewhere. But we now know that this magnitude is actually 1.28 times 10 to the minus 16 joules. Well, there's only one equation that we use when we're dealing with kinetic energy, and that's EK is equal to 1/2 mv squared. And we know that in this case, we can solve for V, and so V is equal to the square root of 2EK divided by m. This is where that whole negative positive thing would get in your way, because if you try to take the square root of a negative number, you're going to end up with an error. And so if we plug in our values now, this is going to be the square root of 2 times 1.28 times 10 to the minus 16, and that's divided by the mass, which for a proton is 1.67 times 10 to the minus 27 kilograms. And once you perform that calculation, you should get 3.92 times 10 to the 5 meters per second. And so what will we do at this speed? Well, the next lesson is going to be all about this thing called the cathode ray tube. And in a cathode ray tube, we'll actually take this particle and we will shoot it between two different plates with a different electric field strength and see how it behaves. So until then, let's go ahead and start doing some practice problems and trying to make sure that we understand these concepts before we move forward. We'll see you again.